All right, looking at some circle theorems now, and theorems around circles. We're going to try and see as many as we can. Okay. Let's start with the first one over here. Okay, so I'm going to put a few circles. The first circle over here, I am going to run the line that runs straight through the center of the circle, which is known as your diameter. And then I am going to form an angle on the outside like that. Okay. If you at any point in time have a diameter like that, then the angle opposite or in this part of the circle, which is a semicircle, will always be 90 degrees. This is known as angles in a semicircle, which means that even if I put the angle over there, that angle is 90. Or even if it's that far, that angle will also be 90. So we can see that each of these angles will always be 90, provided that we have a diameter. This is known as angles in a semicircle, and it basically implies that that's equal to 90 degrees. All right, let's look at another one. If I've got a line which runs across like that, and from the center it cuts through this line. Firstly, we call this line a chord. Okay, we call this line a chord, and this is the line from the center. Let's say C. The line from the center, which reaches a chord and happens to cut it in exactly two halves, will also end up cutting it at 90 degrees. So in this particular theorem, the line from the center, which bisects a chord, bisects means two equal halves in this case, bisects the chord, line from the center is shortened, bisects the chord. So if the line from the center bisects the chord, then the line is perpendicular to the chord. And this could go for a reverse, right? You could write this in reverse. You could start off by, given that this is perpendicular, by the way, what does perpendicular mean? 90 degrees. All right, that symbol over there. So you could rewrite this as line from the center, perpendicular to a chord, will bisect the chord in two halves. So we've got angles in a semicircle, we've got angles at the center, bisects the chord, will also be perpendicular, and angle perpendicular to chord bisects the chord as well. So those are two pretty simple examples. Okay. Let's get another circle going over here. So in the next one here, if I have a line from the center, that's your radius, right? And another one from the center, which is your radius again, and a chord, then obviously I am forming an isosceles triangle over here, because those two are exactly the same. A triangle formed from two radii in isosceles. Why are those two the same? Because this is the radius and this is the radius, even though this is the chord. So I can see that a triangle formed from two radii is isosceles. Okay. We've got angle formed from a diameter as a right angle, or angles in a semicircle from a diameter. Then we've got what is known as the tangent. All right, if you run a tangent to a circle, then this angle will be 90 degrees if this is the radius. If you got a radius, remember a tangent is a line that touches a single point, or shares a single point with the circle as it moves past it. And if it's touching the same point which connects to the radius, then that would be 90 degrees. Okay. So in this case, we can write this as the tangent is perpendicular to the radius. Tangent is perpendicular to the radius. Now, why do we write all of this? Because this ends up as the reasons if we ever ask for it. The tangent perpendicular. All right, perpendicular to radius like this. Here. All right, 90 degrees. Let's continue now. The next one, I'm going to draw a line running from the circumference to the center of the circle on either side, like that. And then from there, reaching out to the opposite side completely like that. Whenever this happens, the angle on the inside becomes double the angle on the outside at the circumference. So the angle at the center is equal to double the angle at the circumference. All right, so if this is 30 degrees, then that would be 60 degrees. If this is 45 degrees, then that would be 90 degrees. It's so weird because when you actually apply this to the semicircle and you straighten out those two arms over there, so if you take this over here and you make it into a diameter, let's say, like that, right? So let's suppose I made that into a diameter and I kept that connected over there. We know from angles in a semicircle that would be 90 degrees, right? And look at this now. The angle at the center is still double the angle at the circumference. The only difference is this is 180 degrees and that is 90 degrees. Okay, and this is angle at the center is equal to 2 times the angle at the circumference. So something pretty long reading. And it works both ways. Sometimes the diagram would look, maybe the circle would look like this. All right, in particular in the case, you've got center connecting. And don't confuse this with cyclic chords. Cyclic chords, all corners have to meet at the circle. So this is not going to be a cyclic chord. This is from the center. Those two are equal, by the way. That's the radius, right? And let's say this angle over here, which is, let's say 200 degrees. And this one would be 100 degrees because the angle at the center is 2 times the angle at the circumference. Okay, so that will be your 2x and it will be your x over there. Angle at the center is equal to 2 times the angle at the circumference. And you can apply this now in many different ways by keeping, let's say I kept the first 2 points intact and I started moving the other 2 points. So let's say I kept the angle at the center over there. I just started creating the angle at the circumference in many different forms. So from there to there, I just created that. From there, and from there to there, it's starting to look like it's got a pattern involved in it. But this angle over here is 2 times each and every one of those angles, and those angles end up exactly the same. And using that understanding, we can then develop the next theorem, which is known as angles from the same arc to the outside are equal. All right, so what does that mean? Okay, so angles subtended from a chord, we could say, like that. That's a chord, and subtended basically on the opposite end, or angles from the same arc. And what is an arc? That's an arc, right? Runs all the way across there. And that is the angle over there. So you can have a chord and the angle, or you can have an arc and the angle. So keeping that 2 points, if you develop another angle at the circumference from that same arc, those two angles are going to be the same. All right, so you can call this angles in the same segment. As well as these two being equal on the other end. We call it y. I could apply this a few times. I could do this way as well, and that angle will also be x. If I go this way, I gotta be careful here, right? If I go this way, then it's not opposite, right? It's not opposite. So it's got to be in the opposite part of the line of the arc. It's got to be running away from the arc. And it's going to be running towards the arc, and it's going to become an obtuse angle. You won't really see that. It's the same. Okay, angles in the same segment are equal. You can move that point anyway all the way across. So there's quite a few circle theorems. We are coming to just a few more, and then we're done. But if we jump into the next one, this one is known as the tangent chord theorem. So if you have that particular triangle in this case, this angle over here is equal to this angle on the opposite side. So what you have to do is find the chord and then go opposite. Okay, so you start at the tangent, find the angle, then you got your chord, then you got your opposite angle. And those two will be equal. And this is known as tan-chord theorem. Right? The angle from the chord is equal to the angle subtended by the chord. Okay? So the angle from the tangent to the chord is equal, and this is the chord, to the angle subtended by that chord. And those two are equal. This is known as, you can call it tan-chord theorem generally. And you can also work it out the other way. So if this is the chord on this side, then that angle there will be equal to that angle. Tangent chord, opposite angle, those two are equal. And that's the tangent or tan-chord theorem. All right. The next one is going to be if you ever have to run two tangents across from a single point, like that, right? And you actually draw these perpendicular radii which meet or dissect that from there. So this is going to be 90 degrees there. It's going to be 90 degrees there. These two happen to be exactly the same. All right, so the moral of the story is that the length of that line is the same as the length of that line. And we know that this is a tangent, and this is a tangent on the same circle. This is the radius, this is the radius. So those two will be equal from the same point. And there's the point over there. So to write this out, we say tangents from an external point are equal in length. All right, tangents from, we can also shorten it, say tan from point equal. All right, depending on your teacher as well, just double check how they would like to have it in an exam. In most cases, these are acceptable. So those are all the different circle theorems that we have discovered now. Okay. There's also cyclic quads as well. So cyclic quads is also part of circles. We'll just quickly touch on that. Cyclic quads is when you actually have a quadrilateral inside a circle. So if I draw a four-sided figure, which is a quadrilateral, inside a circle, where every single corner touches the outside of the circumference, it forms what is known as a cyclic quad. Now over here, this last circle here, I'm creating an exterior angle. Because one of the theorems use this exterior angle over here, and it states that it's equal to the opposite interior angle. The first thing is, when it comes to cyclic quads, I can state that angle A plus angle B equals to 180 degrees. And angle C plus angle D will equal 180 degrees as well. We say that these angles in cyclic quad are opposite angles in a cyclic quad are supplementary. Remember, complementary adds up to 90 degrees, supplementary adds up to 180 degrees. Opposite angles in a cyclic quad are supplementary. So those two angles will add up to 180 degrees. As long as the corners of the quadrilateral touch the outside, that's what will happen. Now we know we've seen angles in the same segment. So if I connect these two over here, it'll form something which looks like a butterfly. But it's basically where that angle is equal to that angle, just to give you a sense of awareness that that angle is equal to that one is equal to that one, and that one is equal to that one. This is angles in the same segment, repeated from previously, right? So angles in the same segment. Or angles subtended by equal chords. All right, this is the chord, and it subtends the same angle. Okay, so angles in the same segment, or angle opposite chord subtended from the chord are equal. Okay. Here we have the exterior angle of a cyclic quad, and over here on this side is known as the opposite interior angle. So that angle will always be equal to that angle whenever you have an extension of the cyclic quad. Now you could have extended any side over here. You could have extended this side. You could have extended this side as well. And if that was the case, then this angle becomes that one. And this angle over here becomes that one over there. In that fashion. But just to keep one so we don't get confused. This particular theorem is known as the exterior angle of a cyclic quad is equal to the opposite interior angle. Alright, that would be the reason that you want to work from me as well. Okay, part of cyclic quad. So we've done all the different parts of circles, such that maybe there'll be different variations of this as